Thank you so much for such a warm introduction. Wow, I wasn't planning on being, of you listing so many of my musical things. So if you do stick around for lunch, apparently I will have the honor of performing for you, with some fingers instead of the mouth this time. So please do stick around. So thank you. It's an honor to be here. It's wonderful to be able to share some of our latest, greatest, I guess, research findings with you here. And there will be time for some questions because this is a pretty information-rich type of a talk. So please keep your questions, and I'll be happy to discuss things with you. So here's the title of my talk, Materials by Design. So I think many of you can relate to that. And then you look at the second part of the sentence, and it says three-dimensional nano-architected metamaterials. And maybe even if you understand what each one of these words means individually, it's a little less clear of why do they belong in the same sentence. So the goal of my talk today is to convey to you why, in fact, they do all belong in the same sentence, and I'll consider my job done if I've convinced you of that. Okay, so I imagine that most of you are familiar with a situation like this. You go to the store, you buy all these things that you absolutely need, and you put them all in the plastic bags, and the plastic bags just weren't strong enough to hold all the things that you absolutely needed. So this is not the only example. For example, we have this wine glass that doesn't quite make it to the toast, to the balloons that pop all too readily, to the, oh yeah, I really meant to have 4 children. And these are all examples of very lightweight materials. They're very lightweight and very thin. And because of that, they're really easy to damage and tear. So let's look at the opposite end of the spectrum. Let's look at the strong materials, materials that we know to trust. So here's a machine that I am very intimately familiar with, and I think many of you are too, as of about 8 hours ago. So here's a Boeing 747. It weighs about 1 million pounds. Well, it turns out that the tremendous expenditure in the airline industry comes from the amount of fuel that it takes to propel a 1 million-pound machine through the air. So if I were to fly to San Francisco, I should have done Dallas, but if I were to fly to San Francisco at the statistics at about $3 a gallon, 5 gallons per mile, my ticket should have cost about $6,000 just to fly to San Francisco. So it's a very last-minute ticket. So already with a Dreamliner, they were able to reduce the amount of materials that they're using for this aircraft. And so it weighs half the weight that the Boeing 747, and you can see that it uses 20% less fuel. So that's a tremendous saving. So what that tells you is that materials that we know to be strong are also heavy and very expensive. Let's look at another phenomenon here. So in California, we use a lot of these. On a day like today, I don't think you should use any of these in Texas, but these are solar panels that are being installed ubiquitously all over California. Now, what happens if this guy accidentally slips off the roof? This is going to be bad news for everybody involved because all of these solar panels are made out of single crystalline silicon, and that's a very brittle ceramic. So if it falls down, it's going to be bad news. It'll shatter, and the guy will probably hurt himself. So specialized materials are also very, very heavy and also expensive. And speaking of heavy materials, do you remember that space elevator that we all talked about a decade ago? Well, as far as I know, we still don't have one. And the reason why is because we don't have the right materials. It's because of this coupling between material strength and its density. When I plotted, this is a very busy plot, but what's important here is this. These are all the materials that we know how to make today. They're plotted here. This is a log-log plot of strength, and I chose to plot the strength, but it doesn't have to be a strength. It can be any other mechanical attribute as a function of density. And what you can see right away is that we know how to make materials that are either strong and heavy or lightweight and weak. And you can't get away from this coupling. Very strong coupling. You can see the metals, you can see the ceramics that are prominently featured over here. And so if you want your material to be really strong, which of course is something that you want for your airplanes or for any structural applications, you can't make them be lightweight. At least right now you can't. So wouldn't it be great if we could get into this target region where materials are both very, very lightweight and at the same time simultaneously very strong and robust? And again, I chose to plot the strength, but it can be stiffness, it can be fracture toughness, it can be many thermal conductivity, many other things. So it turns out that many properties are coupled into density. Now, of course, we can't go beyond the theoretical limit. There are some atomic bonds in chemistry and physics that we would have to wrestle with. But that region is quite substantial. It's a log-log plot, so even a modest increment within this plot already would represent a substantial change. So how do we do that? How do we do that if everything that we know how to make today is already plotted here? So what we do is we utilize the concept of architecture in material design. So just to give you an analogy, so here's the Great Pyramid of Giza. So this is the largest stone-made monument. So you can look at it. It stands about 150 meters tall. So that's pretty tall. Okay, and it weighs about 6 million tons. That's unbelievably heavy, right? And so because of its geometry, its weight at the base is really, really high, and its pressure at the foundation is very, very high. Now, in contrast to this engineered structure, the Eiffel Tower, of course, many of you are probably very intimately familiar with this structure. It stands twice as tall, and it's very, very open. It contains mostly air, actually. And it weighs 1,000 times less. It weighs 3 orders of magnitude less. And so what that shows you, and then hopefully a lot fewer slaves were used in its construction. So because of its geometry, the force on the foundation is much, much lower. So what that tells you is that if you're clever about engineering your structure, you don't have to use so much material. You don't have to make materials that are so heavy. You just have to engineer them properly. And so that's what we do. We began this research in a collaboration with Hughes Research Lab. So this is a microlattice, and it's sitting on the world's most normal dandelion. There's nothing photoshopped here. There's nothing unusual about this dandelion. It's a microlattice that's made out entirely of nickel, and it's sitting on top of the dandelion, hardly perturbing it at all. These are very, very lightweight microlattices. So if I were to hold one of these microlattices in one hand and a feather in the other, and to drop them, it'll fall down slower through the air because it has so much drag and it's so, so lightweight. So now, these are very, very lightweight. But what we're after is not just the lightweight. We're after the lightweight and the strength. And for that, you have to go down 3 more orders of magnitude. You have to go down from the microlattices to the nanolattices. And these are some of the examples of the nanolattices that we make in our group. So you can see we make very different geometries. We have complete versatility over what kinds of architectures we can make. What you also see is that I said that they're 99.9% air. So they're pretty much empty space. And so when you look at them, these are all real SEM images, scanning electron microscope images. There's, again, nothing computerized here. And for those of you who like Doctor Who, here's a nano-TARDIS right here. So it's about the size of maybe 1,000th of your hair diameter or something like that. It's a very small nano-TARDIS. So you can readily see that these are very porous, open nanolattices. And so from that, of course, you can see that they're very open. Now, there's a second part that adds to the porosity, and that is that each individual tube that comprises them is hollow. And that's what you see here. So it's an interwoven 3-dimensional network of these cylindrical shells, so to speak, and whose wall thickness can be on the order of 10 nanometers or so. And everything else is empty space. So when you look at them, you realize that when you zoom in to any dimension in the south, so say imagine you have a brick of this material, and you zoom in, at any point within this material, the largest solid dimension is just that wall thickness. It's just 10 nanometers or so. So this single material embodies every length scale from some nanometers to hundreds of nanometers to microns, hundreds of microns, and then millimeters and centimeters. So if it sits on your hand, it looks like a transparent brick. It's like a solid cloud that's sitting on your hand. It's very, very lightweight. It's a little bit like an aerogel, but it won't crumple in your hand because they're very strong. So I haven't quite convinced you or proven to you that they're very strong yet, and so please keep me to it. What you can see is that we're not limited to any type of periodicity. We're not limited to any kind of isotropy. We can make things that are very isotropic. We can make things that look like dog bone tensile samples, and I'll show you some experiments on that. We can make things that are fractal, where the individual beams are now comprised of these self-similar units. And so you can see right in the center image here that each individual truss member is made out of these self-similar, so it's a fractal. It's a nanolattice of nanolattices of nanolattices. So these are very, very interesting materials, and they embody every single length scale, like I said, from nanometers to many, many microns. And so this is why we feel it's appropriate to call these metamaterials, because their properties can no longer be described entirely by structural mechanics or entirely by material behavior. You have to look at them together in concert with one another. So just to show you, these are real. We made all of them, and then this is the process that we used. And to follow up the previous speaker, this is kind of a souped-up version of a 3D printer, but it can make things that are much, much tinier. And we need to go to tinier to be able to get the strength together with the lightweight, and I'll get to that. So how do we make them? we use this process called two-photon lithography. And the way it works is that it's a laser interacting with a particular polymer. It's a photosensitive polymer. The interaction volume between this laser and the polymer is called a voxel. It's a three-dimensional pixel. And as that voxel travels through space, it hardens the polymer, cross-links the polymer wherever it travels, and everywhere else the polymer remains liquid. The way that the laser interacts with the polymer is that it releases precisely 2 photons in each femtosecond pulse, and the constructive interference of those 2 photons provides a sufficient amount of power to cross-link the polymer. So you have this voxel that's being rastered through a 3-dimensional space, and it forms whatever image you want. I can make a nano version of each one of you sitting in the room here. This is why we have complete versatility over the patterns that we can generate. Now, you can imagine that if there's somebody, a sculptor, that's creating a structure, it's very, very time-consuming. And right now, the biggest roadblock for this technology, for example, is the speed. How do you make it be very, very fast? But for us, complexity comes for free. So it takes the same amount of time to write a simple cubic nanolattice, for example, as compared to a nano version of each one of you. So I chose to show you here this periodic lattice that's made out entirely of a polymer. Now, it doesn't have to be periodic, like I said, just anything you want. But we're not going to go and start building airplanes out of polymers or make many other interesting materials out of polymers. So what we do after that is we conformally coat every single beam member of these nanolattices with a material we actually care about. We have done a number of different classes of materials. It can be ceramics, or semiconductors, or glasses, or metals, or biocompatible material, biomedical materials. You heard my triple M, 3M affiliation, that all of the things that I do begin with an M, apparently. So for medical engineering, for biomedical applications, there's quite a few relevant materials that we can coat these nanolattices with. And what we do, so we usually make our samples in these cube configurations, and a cube has 6 faces, so we expose 2 of those faces, and then we entirely etch away the polymer scaffold that we so painstakingly wrote before. So all this work that went into creating this pattern, we get rid of it. And so what you're left with is a negative of it, like a chocolate bunny for Easter or something like that, right? So it's an entirely hollow structure. It's entirely hollow, and the largest dimension in this solid is just the wall thickness. And that's just controlled by the deposition technique. This process lends itself very well to any kind of semiconductor or 2D lithography fabrication technique. If you can deposit a thin film of it, you can deposit it on this. So it's effectively like a nano ribbon that's wrapped around a 3-dimensional architecture. So now, I did tell you that to get to the strength and the lightweight, we had to go down to the nanolattices. And here's why. Here's why a microlattice can't do it. It turns out that at the nanoscale, all materials exhibit these very interesting size effects. For example, if you look at something very common, look at a very common metal like gold or copper or nickel or palladium or anything like that, and you reduce its dimensions down to the size of about 1/10,000th of your hair diameter, so 200 nanometers or so, it can become as strong as steel. So what I'm showing you here is this universal smaller, stronger phenomenon in all of these so-called face-centered cubic metals. This has now been shown by many, many groups, including, I think, some of yours that are sitting in this audience, both in the experimental and in the computational realm. And you can see that all of these metals land on this universal smaller is stronger strengthening. And so what we can see from this is, okay, so we can take a piece of metal and we can make it very, very small. And all of a sudden, we get 2 orders of magnitude in strength. Well, that's a pretty powerful thing to do. Now, let's take exactly the same metal, say, for example, nickel or gold, and we deposit it in a different way, such that its microstructure is different. So now, instead of being single crystalline, it's now nanocrystalline. So now it has these grains and grain boundaries, et cetera. And all of a sudden, this effect is reversed. So you can see it's exactly the opposite. So it's a more modest size effect because it's no longer on the log-log plot, but smaller is now weaker. So what you're starting to realize is that depending on the microstructure, the atomic level microstructure, the size effect in the same material, in the same metal, can be entirely opposite from one another. So you have this very powerful tuning knob in strength, for example, now, right, as a function of size and the atomic microstructure. Now, the size effect is even better than that. It doesn't have to manifest itself only in strength. For example, if you look at some glasses, we're all familiar with glass fibers, right? What happens if you take a glass fiber and you pull on it? It'll break, right? Glass fibers don't elongate. So these are some special glasses, and I can spend another hour talking just about these materials, metallic glasses. So these are metallic alloys that are entirely amorphous. So you would expect a metallic alloy to be crystalline, but these are exactly not, which is why they're called metallic glasses. Now, my student Rachel just made this maybe 100 nanometer diameter nano tensile specimen, and she's going to pull it. It is made out entirely of glass. So this is zoomed in about 280,000 times. So she's pulling on it, and we're waiting for it to shatter and to break at any point in time now. This is a glass fiber, and please pay attention to this region right here. You can see right there, it's necking, and then it's breaking. And if you were to look at the strain axis right here, you would see that it exceeds 100% true strain. So at the nanoscale, materials that are intrinsically brittle, like glasses and ceramics, become ductile. So everything is upside down. Here's the last example. This is one of these nanolattices that I was describing that's made out entirely of a ceramic. And we're going to push on just a single unit cell. And you can see that it's deforming. And these are all ceramic. So imagine your piece of chalk that's now bending. And it's bending to a pretty substantial curvature over multiple cycles. What happens if you try to bend a piece of chalk? It breaks. I don't know, I'm sure all of you have used chalk before, right? A piece of chalk will snap. And this nanoceramic, which is effectively a nano piece of chalk, is not snapping. So what's apparent here is this. Sometimes materials get stronger, and sometimes they get weaker, and sometimes they stop breaking, and they become a lot more resilient. But all of these beneficial properties emerge only at the nanoscale. So the big question that we had, that we posed in our group, maybe just a couple of years ago, this is a very new field. Architected metamaterials is a new field, and now there are entire symposia at conferences that are dedicated to it. And the idea here is this. Can we harness all of these beneficial properties and somehow proliferate them onto a much larger scale without losing any of them? So this is where the three-dimensional architectures comes together with this nano size effect. So that was the question. Now, to test these, you can't resolve any of these structural features with your naked eye. Like I said, it looks like a cloud, like a brick, a transparent brick that's sitting on your hand. So you can't see all this refined detail, this extra level of organization before you get to the atomic level. So we have to do everything in this special instrument that we built a while ago that allows us to observe the deformation in addition to getting the data. So we have these different inquisition devices. You can see we torture our little samples in every way possible. We push on them, we pull on them. For example, the opening in some of these tensile grips that I'm showing here is only 200 nanometers. So we can really pull on things that are really, really tiny, and then we can also compress and bend things that are much larger than that. So let's see what happens. So this was the question. So this is an example for why this kind of an in situ technique can teach us quite a bit. So this is a hollow gold nanolattice that my former student Lauren is compressing. And so watch what happens. You can see right away that the deformation, all of it, occurs at the interface with the rigid substrate. And this top part of the material doesn't even know that it's being compressed. So wouldn't you like to have this material in your helmet or in your car or in any kind of an application which requires energy absorption, so that the material takes all this impact upon itself instead of transmitting it onto whatever is adjacent to it? Now, we would have never known this if we didn't have this ability to visualize it. Now, we can correlate each one of these individual layer collapse with the undulations in the stress-strain data, which we're collecting simultaneously. Neither one of these pieces alone would provide us with as complete of a set of information as this technique where we can do both together. So this was the question that we posed. So this is a hollow ceramic nanolattice. It has octet architecture, which is an example of some of the stiffest architectures that are stiffest and strongest architectures out of the entire out of the entire kingdom of cellular materials. These are hollow. The wall thickness here is 50 nanometers, and they're made out entirely of alumina. Alumina is the type of ceramic you would use in your furnace, or in the old days people used in your furnace. It's this white powdery stuff, right? So very, very brittle. So imagine your china cup, right? So it's very, very porous and very, very brittle. So it's like your fine china with a severe case of osteoporosis. It's very, very thin walls, right? 50 nanometers. So what would happen if you were to step on it, which is figuratively what we're going to do here? It'll shatter. Right? It's very, very porous and very, very thin-walled. So let's see what happens here. So my student Lucas is compressing this, and it does exactly what we predicted. It shatters. We have a little nano cemetery in our instrument for all of these crushed nanolattices. So this 50 nanometer thick-walled nanolattice crushes and dies. Now, usually in experimental labs, you don't stop and declare victory with a single experiment. So Lucas is going to do another experiment where everything is the same except for the wall thickness. It's the same geometry, the same architecture, the same deposition technique, and look what happens. So he's compressing it, and it should shatter at any moment, and it recovers. So this is I'll play this video one more time. This is exactly the same ceramic, which should shatter even more because the walls are so thin. And he compresses it almost to 50%, and I'll show you much more data, which goes even way past 85% or so, and it recovers. So my student Lucas just made a ceramic that's 99.9% air, that's just as strong as a bulk ceramic would be, and recovers. It's damage tolerant. You can't kill this thing. You could try. We've tried many cycles, and it doesn't. So if that doesn't tell you that there's a size effect, I should just fly back to California right now. So the only thing that's different here is the wall thickness. And now the big question was, would you like to know why this happened? Is there anybody here who would like to know why this happened? Okay. All right. So these are columns. These are all cylinders and beams in a way. And so you can imagine that there are different failure mechanisms. So you could have beam Euler buckling. These are all buckling type of events. So if you have Euler buckling, you would need a continuous solid beam. And we don't have those. These are all thin shells, right? So we don't have this middle situation either where you have the core shell. We have since studied many of these systems. But in this particular case, it's this open type of a cylinder. So it's probably some kind of shell buckling. So it's relatively easy straightforward to show that in these regions of high tensile stress, you can set these failure criteria equal to one another. It can either yield, in which case for a brittle ceramic, remember this is a brittle, very brittle ceramic that's not supposed to recover. So yielding here would indicate fracture, or it can locally buckle. So those are the two things, the two ways that it can fail. And by setting them equal to each other, you can come up with this ratio of the wall thickness T over the radius of the shell, of the beams. And that, for this particular material, for this particular geometry, it turns out that this ratio is on the order of 0.03. Okay, so let's see what happens. So for a 10 nanometer wall, nanolattice, which is what I just showed you, this ratio is below the critical ratio. And what you can see from the data right away, this is where it exceeds 50%. For every single size of unit cell, for every single geometry, the structure fully recovers. If you look at the image here, this is the image of a nanolattice after the deformation, and you would never be able to tell because it's exactly the same. It's fully recovered. Now, what happens as we increase the wall thickness? You can see we get pretty close to this critical ratio, and as we start deviating farther and farther from it, the material can no longer, this guy he's not even trying, the last guy, he's not even trying to recover. It becomes more jerky, it becomes more catastrophic, the material dies. So here's my question to you. Well, if it's all about mechanics, mechanics tells us it's all about the ratio, T over A, right? So what that means is that if we were to scale this up to a giant building like this, the same phenomenon should prevail, right? So if it's all about T over A, imagine that we now scale this up so that the wall thickness is 10 centimeters and the overall radius is about 3 meters, right? So kind of like this futuristic building that I put here. So can you imagine a giant coming here and stomping on this building and the whole building springing back up? I know it's early, but you can't imagine that, right? This wouldn't happen. So why not? How does the size effect manifest itself here? T over A, the ratio, is scale-free. So how does the size effect play a role here? And it really does. Am I not allowed to ask the audience a question? Well, so many of you probably know this and are maybe not answering for whatever reason. So it turns out that it's all about the defects. Materials, brittle materials, fail at defects. When you make something that's 10 centimeters wide, the probability of finding a defect, of finding a million defects, a whole bunch of distribution of defects, and what I mean by that is any kind of an inclusion, any kind of a pore, any kind of a microcrack, is 100%. So when you start deforming this, your material will fail at those locations before it ever gets a chance to experience anything like buckling. But when you make your material whose wall thickness is only 10 nanometers, first of all, the probability of finding a flaw is much, much lower. We're able to make much more perfect materials at these very small thicknesses. And secondly, the size of the largest flaw is only 10 nanometers. That's a very small and a very strong flaw. So this is why the material is able to buckle before it ever fractures. So the way the size effect manifests itself here is by our ability to make materials much closer to ideal at these you can make them as long as you want. You can make them as long as this stage. And as long as the thickness is 10 nanometers and then we're wrapping it around this 3D architecture, it'll work. So we can make, eventually, something that's contained entirely of the nanolattices, that's the size of this building, that will recover. You just can't have your wall thicknesses be 10 centimeters. So, no, right? That was the right answer. So, but the original question was, did we hit the white space? So let's see if we did. This is the original map, to remind you. And all these points, the purple points and the orange points, are our old data. Data is now a year old, and so in our lifetime, it's very, very old. So you can see that we're not quite where we want to be yet. And since then, we've actually improved our process, and maybe some of you can improve this process even further. We're already pushing the way into this white space. It would be great to push it even further. But what that tells you is that it is possible to decouple these properties by controlling both the architecture and the material size effect. And then you can start making entirely new classes of materials that can push this entire, the strength at least of the materials into the white space. So that was pretty exciting. But there's a little trick that I'd like to share with you. I provided some guidelines here, and if my laser pointer would work, I would actually be able to point to it. But you can see that there's this theoretical maximum scaling, right? So you can see that this is a log-log plot, so it's a power law exponent. Now, when you look at the scaling of our purple and orange points, it's not quite ideal. So it falls off more rapidly than it ought to. So we would like the scaling to be linear. In fact, all the analytical theory predicts that, for a stretching-dominated solid, it should fall down linearly, which means that if you reduce your density by a factor of 2, your strength only falls down by a factor of 2. But in our nanolattices, it falls down by a factor of more than 2. And in fact, the scaling, instead of having the power of 1, it's 1.6. So what's going on? So it turns out when I told you that it fully recovered, it recovered by about maybe 99.8%. But we did accumulate some damage. And when you look at the zoomed in area right here, there's a crack that's forming. So it turns out that these nodes is really what's killing us. So when you compress it and then recover it, what happens is that in the first cycle, you pre-damage your nanolattice. So you form these tiny little microcracks that are sitting in the nodes. And then after that, they just sit and open and close, open and close, open and close. So that's why you're able to recover them over multiple cycles. But we still do generate some damage, and this is why the strength is falling off faster. But we figured out even a way around that. And this is your people's beautiful journal that we were particularly proud to make it on the cover. Turns out that just like in the nano world, everything is upside down, smaller, stronger, and et cetera. It turns out that if the nodes are the things that are killing you, you should just make a lot more nodes, and then it'll work. So what we did is we made these hierarchical nanolattices. So in a fractal-like construction. So what I mentioned earlier is that instead of each beam just being a shell in itself, you can now fractalize it and make each beam be composed of these self-similar or not self-similar units. You can see we got to about third order of hierarchy here. And so when you compare, this is kind of a busy plot, but this is our data from before. The slope here is 1.6. That's what was killing us. And now that we made them be fractal, look at that. We got to the ideal scaling in both the Young's modulus and the strength. So not only did we buy ourselves 2 more orders of magnitude in density reduction, but we also got ourselves to ideal scaling. So like I said, it turns out if the nodes are the thing that's damaging to you, just make a lot more nodes in these hierarchical nanolattices, and you can get the scaling to ideal. The real reason for why we're able to do this is because it suppresses any kind of local instabilities, right? So it's just like a crane. So anytime you compress a beam, you could have a local instability at a node. But now if you fractalize it, you basically diffuse that. And so you now are not as susceptible to local instabilities. And just to show you, so this is a very, very brittle ceramic, one of those fractal nanolattices. So this is half a unit cell because it takes about a century to write one of these. Not anymore. But you could see that each individual beam member here is fractal. And so Lucas is compressing it, and you can see this giant kink. So this is where you're expecting the material to snap at any moment now. It kind of hurts me every time I watch this video. And bam, it fully recovers. this is a ceramic for you. So yes, everything really is different at the nanoscale. Now, this is a third order hierarchical nanolattice, and one of the questions that I often get is, how many times can you compress it? And so, for example, you can compress, we have never, anything that compresses, that recovers once will recover many, many times. We have never been able to kill something that recovers once. So if it recovers once, it will keep on recovering. Now, watch what happens here. Your first cycle is always a little bit different from all the subsequent cycles. So cycle 2 through n is about always the same, and the first cycle is a little different. This is what I mean by the pre-damage. So in the first cycle, you basically introduce all the damage and all the microstructural changes that you're going to introduce in your material, and after that, it's just repeating this behavior. You can see this characteristic hysteresis. So you are actually absorbing quite a bit of energy. And this is just one example, and you can certainly tune them to be as energy absorbing as you need them to be. So a few words on fracture, if we have a few more minutes. So far, everything I've shared with you has been in compression, right? In shock. So you can imagine applications like energy absorption, shock absorption, any kind of maybe microfluidic type applications. But what I haven't really told you is, how are they damage tolerant? Well, to do that, what we really need to do is to do some fracture experiments, right? How do you do a fracture experiment on a material that's both discrete and continuum? It's just like the particle-wave duality of light. This is both discrete and continuum. If you zoom out, to you, this material looks like, like I said, a transparent brick, so like an aerogel. But when you zoom in, it's all nodes. It's all discrete. So how exactly do you define a flaw? So we've been working with some of the people who really know a lot more about fracture than we do, and they don't know either. So if that's any consolation. So, well, we really tried. So we fabricated these nanolattices with the prefabricated notches in them. So you can see right here. Here's a prefabricated notch. These are real images again. And so that's a typical fracture experiment. So you put in a hole, you put in some kind of a notch, then you pull on it, and they should all be weaker, and they should always break at the notch. That's kind of how fracture generally works. So this is, just to compare, this is a tensile experiment. So there's no notches. There are no notches in there. We first need to understand how these nanolattices behave under tension, right? So it's very difficult to pull on them. We figured out a way to pull on them. And so you can see that it fractured right here. Whoops. It ripped off their head right here. And you can see that at the load of about 2 millinewtons. Millinewtons or micronewtons? Millinewtons. 2 millinewtons. OK. So now, here's what we're going to do. We're going to use exactly the same geometry and prefabricate a notch in here. Here it is. Here's the notch. I put a little red arrow there so you can see. Now, this nanolattice should break if fracture mechanics works, it should break right at the notch, and it should break at a much, much lower load. So let's see what happens. OK? So we're watching it. We're pulling at it. So this is a head that we're gripping, and we're pulling at it now. OK? So no more pushing. We're just pulling at it. Bam. It breaks at a notch. So this is exactly as predicted. But look at the load here. The load here is 2 millinewtons. So wait a minute, so when they fracture, they don't care if there's a notch in them or not. They always fracture at the same load. So it turns out that there's something not quite right. So it broke at the notch, but it broke at the same load, and it's not, so it didn't weaken the material. Let's look at the last example here. This is a slightly smaller nanolattice. And so again, we prefabricated a notch, right where the red arrow is pointing. You can see that's where the notch is. And we start loading. We now know that it's going to break at the notch, exactly where the red arrow is. And it doesn't even know that the notch is there. So what we're learning from these nanolattices, I'll skip through the details here, is that there's a way to design them in such a way that they're totally insensitive to flaws. What I'm showing you here is the stress at failure is a function of, this is a very common thing in fracture, is a function of the ratio between the crack size or the notch size over the sample width. So basically, what percentage is the sample pre-notched? And what you see is that there's a regime. And again, if my laser pointer were cooperating, I would show you this. Here it is. So there's a regime where these nanolattices become insensitive to flaws. Their strength doesn't at all become lower with the presence of flaws, and they don't break at the flaws. So these nanolattices are everything that you ever wanted. They don't break. They They are insensitive to flaws. They can be made out of any material that you want. They're energy absorbing, and aside from bringing you coffee in the morning, they can really revolutionize the way that we think about making materials. You have so much flexibility over everything, over the geometry, the architecture, the type of material. You can design them to do exactly what you want them to do. And so I want to spend just the next few minutes telling you about some of the real applications that we have endeavored upon. And perhaps you can come up with a few more, but there are so many of them. For example, in energy storage, we've started making battery electrodes out of these. Because, for example, on the anode side, there's a tremendous push by Tesla and by everybody else to start making the anodes out of silicon instead of graphitic carbon. Because silicon can store an order of magnitude more lithium for the lithium-ion batteries. But the problem with silicon is that when you try to shove all this lithium into it, it undergoes a 300% volumetric expansion. So what happens when you try to volumetrically expand a very brittle ceramic? Well, it cracks. This is what happens. The picture at the top there with all the cracks. So what we did is we actually made these nanolattices into battery electrodes. So instead of being hollow, they're now made out entirely of copper with a silicon wrapped around it. So your copper is the electricity conductor, and the silicon is the active material. So my student Xiaoxing, watch this, he figured out how to rig our instrument to lithiate. And you can see the lithium all going in, and the structure expands by about 200% with no fracture. So these nanolattices, and here's the delithiation. So it goes over multiple cycles. And here's some data. For those of you who are in the battery world, it really is functioning as a battery. This is not the world's best battery. I'm not necessarily advocating that we start using these to make batteries. But what I am suggesting is that we can make battery electrodes that are exceptionally lightweight, that are exceptionally mechanically robust, and that won't crack upon lithiation and delithiation over multiple cycles. You can also very precisely control your surface area, which is where all the electrochemistry happens. Now, this is one application. If you look at the world of biomedical applications, I only chose to show you these images, but there are so many. For example, we are now making implantable batteries. So we're working in the collaboration with the City of Hope. So imagine you have, actually don't imagine that you have a tumor. Imagine somebody else has a tumor, and you're trying to track its development. You can't really image a tumor every single day in your body. You would have to go to the MRI or a CAT scan or something like that. What we can do now is we can inject, without any invasive surgery, these RFID tags, effectively, these active RFID tags on a liver. And they will constantly be transmitting every day. They'll be collecting the location information. And so all the surgeon has to do is get the readout from, say, 30 of these active RFID tags to understand the development of the tumor. Is it growing? Is it shrinking? Is it doing anything else? So no more invasive. So imagine in a third world country, you can't go to an MRI scanner every day. You can't get yourself monitored like that. So another application is that these nanolattices provide a very lucrative scaffold for cell growth, human cell. So these are all osteoblasts, your human bone. And so you can see that these osteoblasts are populating these scaffolds, so we can start writing the actual bone material. So these are just some of the examples. Now, I work at Caltech, and at Caltech, you can only major in physics. You can think that you're majoring in something else, but you're really majoring in physics. It can be physics with a double E flavor, physics with a material science flavor, physics with a mechanical engineering flavor, but it's all physics. It's more specifically applied optics. We have, for some reason, a very diverse department of applied optics, so we had to work on some photonic crystals. It turns out these nanolattices are actually photonic crystals. And so when you push on them, they change color. So what I'm showing you here is that they're very sensitive to strain. So this photonic band gap that emerges in these just by the virtue of geometry, we don't have to worry about the material. It's just because they're so periodic. So this Bragg spacing starts to shrink as you push on them, and it changes color. Imagine you put this in your e-ink and you start printing money with it. And if you put your finger on a particular part of the $100 bill, it changes color. That's what these things enable you to do. And they're small enough that you can put them in the nozzle. And this is the last example, and this is probably the one that I like the most. And that's biomimicking. What I'm showing you here is in the top row, these are all real biological materials. This is a diatom. So it's a little creature. Actually, nobody really knows why diatoms exist. They're a little bit like grass for sea creatures. These are tiny little things, and you drink them in your water if you don't purify it a lot. These are anywhere between maybe 30 microns to 100 microns in diameter. They're beautiful little creatures that are made out entirely of silica, so glass or sand. They have these beautiful arrangements in them, in these hexagonal pore patterns with little cookie cutter type walls. And nobody knows why. Why did nature that's had millions of years of evolution made them like this? And we don't know why. And then if you look at the butterfly wing, and you zoom in, you can see this is a so-called kegome lattice in 2 dimensions. So kegome lattices turns out that they're particularly resilient to fracture. So of course it makes sense for a butterfly wing to be made out of these kegome lattices because a butterfly would die. Its functionality, its life, depends on its ability to not fracture, to not tear, right? We have no idea why nature made these materials to be architectured in such a precise and careful, obviously very carefully engineered way. In this inverse problem of trying to understand why these materials are so robust and resilient to damage, it's too complex because we can't isolate a single parameter. We don't know what things are there for the biological functionality, what things are there for the mechanical robustness, and why it's constructed this way. But what we can do is we can solve the forward problem. With our nanolattices, we can now make materials that exactly replicate both the architecture, the geometry, and the material, and the dimensions of the real biomaterials. So just to show this to you, I'm showing you these 3 images. And I'm going to tell you that maybe all of them are biological, or maybe all of them were made in our group, or maybe one of these things is not like the others. And I invite you to suggest which ones are which. And people always have many guesses. In fact, I'm kind of hoping that you're wrong. So we made the one on the right. That means that that's right, because you were paying attention, because I showed that image before, right? Thank you. This is a softball. So then the question is between the middle and the one on the left, right? Well, you don't have to answer me now, and actually, if you're interested, I'll share it with you later. But you're thinking about it, and it's not so easy to tell. You're looking at all these, and you're like, I don't know. They could all be biological. They could all be, you could have made them all. We don't know. That's the point. That's the whole point. We can now start making materials that are exactly like the ones that nature makes, and we can isolate each single parameter. So just to show you, so this is a diatom. We actually took it apart, and we were lucky enough to yet again publish in PNAS. So it turns out that these diatoms, which are very precisely architected, we tested their stiffness and their strength. We carefully extracted a little part of a diatom. Right here, well, I say we, my students did. And then we put it into this configuration over a well, and then we compressed it in the middle to see how it fractures, because each one of these carefully placed holes should serve as a stress concentrator. And so it turns out that when you put the strength as a function of density, so the specific strength, onto the plot of all the existing biomaterials, these diatoms are much higher than anything else that's ever been reported. Why the heck did nature design them this way? We don't know. We really don't. And they're stronger than antlers, they're stronger than bone, they're stronger than a lot of materials that have been thought to have the highest specific strength. So that tells you that nature has plenty more stuff for us to do. So I'd like to finish by summarizing here that if you walk out of here thinking, okay, she showed us some pretty pictures and I still have no idea what this was all about, this is the key message. If you're careful about 3 things, the architecture, the nanomaterial size effect, which emerges in each type class of materials, and the atomic level detail, or the microstructure, you can start making entirely new classes of materials with properties that have always historically been coupled with one another, which are no longer coupled. You can design exactly the material that you want. So instead of being a slave to the furnace and to all of these materials that we now know how to make, we can now say, you know what, I want these properties. And so these are the different possible ways of how I can design them. And the reason why we would want to do this is so that in this world where all of our children are growing up, some of which happen to be mine here, we won't need any hearing aids. We're just going to be able to write the little cochlear bone and put it directly in your ear, and you won't need to have the hearing aid. Our iPhone 83 is going to last for a year on a single charge. Our balloons are going to be helium-free, because with these nanolattice materials, we won't need to fill up the balloons with any kind of gas. We can just evacuate all the air, because vacuum is lighter than air, and these things are stiff enough where they can withhold that vacuum and go up into space. Of course, none of our Christmas ornaments are ever going to break again. And this is our latest pursuit. So I imagine maybe we'll become intimately familiar with some of these over lunch. These are brownies. So our current pursuit is chocolate nanolattices, which are 100% taste, 99.9% air, and 0.01% calories. Thank you. And of course, a huge thanks to my group, my very silly group, and all the funding sources. And I'm happy to answer any questions.
Thank you, Julia, for a fascinating talk. We have time for a few questions, if you're willing to sacrifice 2 or 3 minutes of your coffee break. Instantly.
I know you.
Thank you very much.
Thank you.
Can you tell us how you design the microstructure? How do you know the microstructure?
So the question is, how do we know the microstructure? We use transmission electron microscopy to study all the materials. So TEM, which is a technique that allows you to effectively view the individual atoms. And well, we know what kind of microstructure we would get with each deposition process. So if we want a single crystalline material, we would use MBE, for example, molecular beam epitaxy. If we want something that's nanocrystalline, we would use electroplating or sputtering. So based on what? So how do we design the architecture? Is that what you mean? OK. So for material scientists, microstructure is the atomic level detail. And I think the question is architecture. Yeah. So the way we design the architecture is specific to the application that we want. For example, if we're working on strength, we would choose a stretching-dominated solid. So there are different classifications of cellular solids that you would use. For strength, like I said, for something that's energy absorbing, you may want to use a bending-dominated structure. An example of that would be an octahedron. If we want to work with an isotropic structure that's very strong, we would choose a stretching-dominated solid, which would be an octet, like I showed. If we're looking for working with the cells, I showed this truncated dodecahedron because the cells need to be able to fit into it. So we choose the architecture based on what we're studying. Thank you.
Yes.
Your talk was a beautiful example of arts and science.
Thank you.
But is it in the constructing very low or high porosity materials, is there a possibility of preventing convection by structure?
So heat convection.
Yes.
Yeah, because you can design the surface area to be, so that's tricky because convection is proportional to the surface area, right? So in all of these porous nanolattices, the surface area to volume ratio is very high. So what you can do is possibly protect them. So one part, this is only about maybe 20% of all the research that we're doing right now. One thing would be thermally insulating materials, right? So then you can specifically design your material, design your nanolattice so that it's less susceptible to convection because you can encapsulate it. For example, right, you can build little heat exchangers where the nanolattices don't have to be made out of a monolithic material. You can have multi-layers. So you can have a thermal barrier layer or something like that over them to protect from convection or something like that, from losing heat to the environment.
One more question there. Yes.
I was wondering about the effects of temperature. As you mentioned, the defects play an important role in generated by stress, but stress generated by heat. And I wondered whether that, for example, was really limited, making the things even thinner than you layers.
So the heat effects are, so the question was about how does the heat contribute to these, right? So, you know, it's very specific to the material class that you're studying. For example, we've done a bit of work on going down in temperature and looking at the cryogenic behavior of these. And we discovered some very interesting phenomenon because, of course, we know that there's a ductile to brittle transition that all materials undergo when you lower the temperature. Well, for the nanolattices, that temperature is lowered. So even if you cool them down to cryogenic temperatures, sometimes they're still unable to recover and exhibit deformability rather than brittly fractured. So there are interesting effects, of course, as a function of temperature because, like you said, it affects the defect behavior and it affects the surface diffusion, for example. So definitely temperature effects play a significant role.